Okay, we're continuing to talk about hashing. Today, homework 3 will be out sometime today. It's just Cinda has to look it over, so I'm waiting for that. And then midterm 2 is November 7th. Oh, by the way, homework 3 is due 2 weeks from when it goes out. So it's not a longer homework, it's just we're going to give you more time. So there's several overlapping assignments that are going to happen, but they're all going to be spaced out in a way that will let you manage your time yourself as opposed to us managing your time. At least that's the plan. And what could happen is that you just delay until the very last minute, which would not be good, but that's what's happening. And programming assignment 2 is due in November 1st. Today we're going to talk about universal hash functions and also about collision resolution policies for when things collide in hash tables. But before we do that, we have to warm up. And the warm up today is you're going to be somebody who's trying to crash a server that's running a hash function that you happen to know. And I put down 2 hash functions here to play with. The first one is 2k plus 7 mod 10, and the second one is 2k plus 7 mod 11. And so, just like to give you a chance to find keys that hash. I want to find lots and lots of keys that hash to the same location, they collide to the same location using these hash functions, because I'm evil and I want to crash somebody's server. So anyway, I'll give you a few minutes, maybe actually just 2 minutes, and come up with a lot of keys that hash to the same location. We're trying to find lots and lots of keys that hash to the same location using these 2 hash functions. Everybody good? Looks like a lot of people are just looking at me. All right. What kind of keys hash to the same location using this mod 10 version? This one right here. Yeah. I beg your pardon? You want to choose k to be a multiple of 10. Okay. That'll work. Because you'll get, if I choose k to be a multiple of 10, I'll get, well, like for example, if k is 0, I get 7. And if k is 10, I would get 20 plus 7 modulo 10 is 7. And if I choose k equals 20, then I get 40 plus 7, which is, so I could choose all values of k. Let me write it up here. Choose k to be 10 times I. So choose for all values of I that you'd like, or any integer I. And they will collide. But actually what I really wanted you to do on this little warm-up was to try values and to see where they hashed. So that's what I'm going to do. I mean, this is brilliant. This is exactly the right answer. But I want to look at this like a picture, like a clock. And I have this thing, I'm taking it mod 10, so I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 around my clock. Because it's mod 10, it's always going to be one of these numbers. And if I start off at k equals 0, for k equals 0, I get 7. And for k equals 1, I get, thank you, 9. 9. And for k equals 2, I get, is this too easy? This is like, you know, my daughter is in 7th grade. She's doing this mod stuff right now. So I know you guys knew it. At one point, 1. 2 times 2 is 4 plus 7 is 11, and 11 mod 10 is 1. So what am I doing here? Now when I go to 3, where am I going to go next? 3. Where am I going to go next? 5. Where am I going to go next? And now that's it. For this hash function, 2 times k plus 7 mod 10, those are the values that are produced by choosing k equals 0, 1, 2, 3, 4, and, well, did I do 5? Yeah, 5. No. 0, 1, 2, 3, 4, 5. I did 5. And then what happens? What about 6? It goes to 9. And 7? We'll go to 1. And 8, it will go to 3. And 9? This is very interesting. It's like one of those spiral graph things that's really boring because it's repeating the same thing over and over and over again, and it's missing a lot of the digits, well, a lot of the numbers like 2, 4, all the odd ones. It misses all of those. So that's interesting. It's not a very nice hash function because it doesn't cover the space of hash functions, and it makes it kind of easy to find lots of numbers that collide. We just have to take anything, in this case, anything that's not even 10 times I, we could just choose 5 times I, and it would work. You want it to? What about this hash function? We can draw another circle like this. Maybe 0, 1, 2, whoops, that's a 2. 2, 3, 4, 5, 6, 7, 8, 9, 10. What happens when I do this? I start at 7 again when k is 0, and then what happens? You know, each time I'm multiplying k by 2, so if I increase k by 1, this number goes up by 2. So I'm just moving two units around the clock each time. So I just tick over 2, I tick over 2, tick over 2, tick over 2. Are you expecting me to, well, you missed. We didn't hit again. We went around, we go around, we go around. Until eventually, did I make a mistake? Oh, yeah, I made a mistake. I forgot about 5. That's a much prettier spiral graph picture. And it represents the fact that the number 11 and the number 2 are relatively prime. So if I take 2 steps around the 11 clock, I will visit all of the numbers around the 11 clock because 11 and 2 are relatively prime. If I walk around the clock, the 10 clock, if I walk around by 2, then I don't visit all the numbers because I get stuck because 2 divides 10 evenly. So one might say, in fact, many people say, this is a better hash function than this hash function. What do you think? Which of these two hash functions is better than the other one? And why? Yeah.
Let's say the second one.
So the second one, why?
Because there's more values it can be hashed into, I guess.
Yeah, that's right. So actually, the real advantage to this hash function is that it's using all of the slots in the table, whereas this hash function uses only half of the slots in the table. It's like that dice game we were playing before, where everything that we were hashing was to an even number. So in some sense, the good thing about this one is that it uses all available slots. And so if you were in a situation where you were thinking that numbers were coming in a nice way, your hash table might be used more fully. All of the slots might be used in using that hash table over using one in which you don't even get the chance to hash into a particular slot. So that might be a reason why it's better. Anybody else have any other reasons why the first one might be worse than the second one? It's a smaller range. There's only, in our table, there's only 10 possibilities for the first one. There's 11 possibilities for the second one. Does any of this matter? I mean, what's going to happen when you release these as your hash? When you release either one of these as your hash function, what will happen nowadays? Someone will go and find your hash function, and they will crash. Unless you trust the people using your hash function, or unless it's in their best interest to make the hash function work well, this hash function is terrible. Both of them are equally bad. Because I can find a sequence of numbers that will cause the first hash function to crash, and I can find a sequence of numbers which is just everything 11 times I for I in integers that will crash the second hash function. But both of these are bad. Fixed hash functions are just bad, unless you're trusting. Now, it's okay to be trusting. In fact, I showed you Yak's hash function last time. The reason why Yak still has the same hash function, that fixed hash function that's sitting in there, is because they don't care. They don't care about denial of service attacks. If you're using Yak and you decide to be evil and malicious, who gets hurt? You do. It's going to slow Yak down. That just means you're not going to be able to do the work you wanted to do because Yak is a tool to build compilers. And it'll take you longer to build your compiler. So if you decide, oh, I'm going to be clever, I'm going to name all of my variable names capital XY and little xy, and shuffling those things around. Bad idea. You'll suffer. So Yak doesn't care. But if you do anything on a server today that uses a hash function, then you don't want to use a fixed hash function. You want to use what? A random hash function. You want to use something that's selected specifically for the table that you've instantiated at that time, that nobody can guess precisely because it's chosen from a large enough set of hash functions that it makes it hard for somebody to guess what you've chosen, but still has a nice property of sort of spreading the keys out nicely in the hash table. So we're going to look at we're going to look at a definition of a universal hash function set, which has this nice spreading out property, and then we'll look at an example of that to sort of see what could be done in practice. So this is saying that I have a set of hash functions So there's a bunch of hash functions to pick from. And it's called a universal set if it's true that no matter what two keys you pick out of the universe of keys, so x and y are two keys, and they're different, no matter what two keys you pick out of the set, the probability over the random choice of hash function, so I'm pulling a hash function out of this bag at random, the probability that that hash function happens to make those two keys collide is perfect. What does perfect mean? Well, if I have a table of size m, what's the best that I can hope for? If I pick two different keys x and y, what's the sort of best probability that I can hope for that those two keys would collide? I mean, it's sort of like that question I asked you about the lottery. Remember, there was like one key got hashed into lottery location 3,822. What's the probability the second key is going to get hashed into that location? 1 out of m. So we're looking to try to make that be true for every pair, for any particular pair, x and y. You fix that pair. If you draw a hash function at random, it will keep those two separate except with probability 1 over m. At most 1 over m. That's what it means for this hash family, this set of functions that I'm picking hash functions from. That's what it means for it to be universal. And these are good properties because we don't want there to be high probability that certain keys map to the same location, because somebody could do a denial of service attack on our hash function. Before you read the next part of this slide, do you happen to know of a set of hash functions that is universal? The property is that if I pick two functions from that set at random, the probability that two different keys collide is 1 over m, the best possible. Do you know of a set of functions that has that property? You do. 2k plus 7. Oh, this one? Possibly. If your keys were really small, that would be true. The keys would have to be less than 11, because otherwise I can crash this thing. So it is true, but usually I think of 11 as being small. And no, this is a set of functions that you knew when you walked into this class. If I pick two functions from this set of functions at random, then I get a collision with probability 1 out of m. These could be a really big set of functions. Could be lots of them in there. That's kind of a good thing. If the set is really big, that's a good thing because it means that there's lots of randomness going into the selection of the functions that are doing the hashing. Yep?
So yes, but hash x equals x.
Oh, you mean just hash it to itself? Oh. Well, again, you better not have more items that you're hashing than the size of your table, because it can't be a function that doesn't map onto the m slots that are in your table. But your function would work if I knew that, so he suggested the identity function, which is just one function, and if that identity function, which maps its key to a slot, which is exactly its key value, if that identity function was guaranteed to operate on a set of keys that was smaller than the size of your hash table and mapped into the locations between 0 and m minus 1, then you're great. But sadly, that really doesn't happen very often. Typically, you don't have those kind of keys. usually have big keys. How about the set of all functions? All functions that map keys to indices in the range 0 to m minus 1. So this is all functions from the key space to the set 0, 1, the indices into your hash table, 0 through m minus 1. How many such functions are there? If I have, let's suppose that my keys are smaller than p and greater than or equal to 0. So p is some upper bound on how big the keys can be as a number. It's usually p is pretty big. How many functions are there that take keys to the number 0 through m minus 1? Yeah.
Is it an infinite number because you can always have any function y, say mod n?
No, it's not infinite. It's a function that depends on m and p. If the number of functions that will take you from key space to 0 through m minus 1, it's a function of m and p. Do you know what that function is? Yeah. M to the power p. So how would I write down one of these functions? There's a function that's taking a set of numbers from 0 to p minus 1. It's taking those numbers to numbers 0 through m minus 1. How would I write it down? Well, I'd say, okay, well, if you wanted to take 0 to some number, it's going to take it to, so this is 0, 1, 2, blah, 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 blah. I'm going to write a chart, p minus 1. And I write down where it's taking us. This is the key. This is the slot that the key goes into. And what can I write down for the slot for item number 0? How many different things could I write down there? How many different slots could it go to? M of them. I could write down 0 through m minus 1, 0 through m minus 1 right here, but I have m choices. So this 0 means m choices. And how many choices after I write that one down do I have for this guy? Yeah, m. And for this guy, m. And for this guy, m. And how many m's did I write down? So I have m choices, and I can make any choice for the first one. I can make any choice for the second. I can make any choice for the third. How many different possible choices do I have? It's just the product of all of those things. So that's m to the p. M to the p is the number, so this is equal to the number of functions from keys to slots. But you understand that the number of keys is p and the number of slots is m. From keys. And that's a lot. The problem, we could use all functions, because now if I look at any two particular items, x and y, two particular keys, and I picked my function at random from this set of functions, I'm choosing basically every possible way of mapping x equally likely and every possible way of mapping y equally likely. So the probability that those two things collide is exactly like this lottery ticket thing. It's the probability that somebody's chosen the same number in California as they chose in Illinois, and that's just 1 out of m. So why don't we just use the set of all functions? as a universal hash function. It is a universal hash function, a universal set of hash functions. Why don't we use the set of all functions? Now you have to put your practical hat on. We have to be practical now. Yeah.
For our purposes, even if two functions don't have the same like implementation or whatever, if they map all of the values from 0 to p to the same values, then for us they're the same. And there's so many different combinations of mappings. And that's what we care about.
So we care about collisions.
Yeah.
And collisions will occur if two values, x and y, two key values, x and y, map to the same location.
Yeah.
And the probability of that occurring for a randomly chosen function from the set of all functions is exactly 1 over n. So that's pretty much as good as you're going to get. Unless you form a perfect hash function, which is cheating, because you actually know what the keys are. So if you don't know what the keys are, you only know that there's a key space that's really, really large. This is the best you can do. So it's not that it's not functioning. It won't function as a bad hash function. It will be a great hash function, except for one practical difficulty. How do we use it? How do we write it down? How do we record? How do we use this function? I give you a key. What do you have to do to calculate this function? It's not like a nice function. It's not like multiplication. It's not part of your library of C++ math functions. It's not there. What do you have to do? I give you a key. You have to find out what the value is. You have to look it up. And you have to say, I have this key, key number 2, that came in. I have to look up what my function says is the value for that key. Does this sound like a problem that's you've heard of before? I give you a key, and you've got to look something up based on that key? It's hashing again. I mean, in order to calculate this function, in order to calculate this perfectly lovely hash function, we have to perform hashing. There's just too many functions. We can't calculate it except by doing basically a table lookup. And that doesn't work. So we need something that uses mathematical operations that are simpler, that don't involve lookups. And so this is one of them. This is one example. There are many universal hash functions. This is maybe the simplest one. It looks an awful lot like what we saw on the previous page. Right here, it's just doing what we did before. It's multiplying the key x by some constant a, like 2, and then it's adding some other constant b, like 7. It's exactly what we did on the first page. We take that mod p, which is now mod the number of keys there are in our universe of keys, which is a big, big number. And then we take that mod m, and p is prime. We've chosen p to be prime so that we don't have to worry about a and p sharing any common factors. So p is a prime number. And once I do this, I take it mod the table size, m. And that's it. Yep.
So how does the set of all functions in the key space satisfy the property that probability is that?
If I look, so the property is I pick an x and I pick a y that's different. So it's like saying I'm looking at two different keys in my key space, and I look at what the values are associated with those keys by the hash function, but I pick the function at random, uniformly. And so what that means is that whatever value is in the first slot is equally likely to be any one of the values from 0 to n minus 1. And same thing is true for the second slot. I look in that slot, I'm going to see, if I've chosen the function at random, I'm going to see each of the possibilities in that slot with equal probability.
So, and in this case, like, keys don't have to be integers, right? Like, can they be like characters?
But eventually, you're right, you're absolutely right, but eventually they're going to be viewed as being numbers. For this calculation to work, we have to view them as numbers. And so we can convert them into numbers by doing whatever you'd like, but we have to convert them into some sort of number. And in order for the hash function to be fast, we want to convert it into a sort of a small number.
Wait, sorry, and then what was like the practical reason why we can use like small functions?
How would you calculate the function if I give you a key?
Yeah, because you're not like defining it.
Well, let me ask a simple question. How would you generate the function? You have to generate this function that you're choosing at random. What would you do? Well, you would just write down a number for each one of these keys. And you choose one of the m values that could possibly be associated with key 0, and you'd write it down. And you would write down the sequence of numbers. That would be the description of the function. And now when you ask to calculate using that function, you have to look up what the answer is for the particular key you're given. And that's what's hard. Because that lookup is exactly what you're trying to do. You're trying to hash. You're given a key and you want to put it into it. It's just so if you could do this, then you wouldn't need a hash table. Because if you could do the lookup, then all you have to do is do the lookup and write a 1 down and say that guy's here. So you wouldn't have to do hashing. You've already done it. Yeah, everybody's so quiet. It's sort of like, I think we've stepped into some sort of alternate math universe. And now everybody is really shocked that we're doing this. This is modulus. Why is this?
But for the 1 over m, do we actually interpret it like a conditional probability? Like, given that we know the value of hash x, the probability that the function we use to compute hash y equals that is 1 over m.
No, it's not a conditional probability, except if you think of conditional probability as being that I've chosen this hash function at random from the set of all hash functions. But it's more like you're saying the probability over random choices of hash function that key x and key y will collide is 1 over m. And this is true for all values of x and y, for all keys x and y, as long as they're different. Yeah?
One last question. So like in previous classes, we discussed how, like, sort of the reason why it's not, the probability isn't 1 over m squared. But I was thinking, like, in probability, like, if we want to calculate the likelihood that both, like, x and y occur, don't we multiply their individual probabilities together?
For two random events that have their independent random events, and one occurs with probability, like for example, a coin flip. If I flip a coin, it probably has probability 1/2 of landing heads or tails. Though I knew somebody actually that could flip a coin so that it always came up heads. And it looked like, anyway, never mind. So they're flipping a coin, and your first coin flip has probably 1/2 of coming up heads. And your second coin flip has probability 1/2 of coming up heads. What's the probability that both coins will come up heads?
A quarter.
Right. But now, suppose that I ask you, what's the probability that those two coins both come up the same? That they match? Well,
But isn't that kind of similar to the previous question? Because earlier you were asking what's the probability that they both come up heads? So it's a quarter.
yeah, no, I'm asking you, what's the probability that they both come up the same? Not that they both come up heads, but that they both come up the same.
Oh, I have to consider all of the possibilities.
And there are m possibilities, and when you multiply m times 1 over m squared, you get 1 over m.
Oh, I see.
Okay. Shall we talk about hashing more? Anyway, the point of this is that the number of random choices that I'm making to describe this function is much smaller than the random choices that I made to describe the general function that I've chosen from the set of all functions. This requires me to choose the value a at random and the value b at random. And those choices are made from A is chosen from a set of size p minus 1, B is chosen from a set of size p, and after I do that, I just use this formula with those random values plugged in for A and B as the selected hash function. And this gives me probability at most 1 over m that two values will hash to the same location if they're different. Okay? One last question on this slide before we leave it. What are the number of hash functions in this family of hash functions? What are the number of possible hash functions that I could generate in this way? In other words, how big is my family of hash functions? Something like p squared. It's going to be actually, I have p minus 1 choices for A, and I have p choices for B, so this is equal to the number of hash functions in this family. So in this universal set. Okay. So now you know what to do. You generate functions at random, but in a particular way so that they're nice. And this is one particular way. Yep.
Sorry, so how do we know this one also satisfies the property of universal?
Do you want me to prove it?
Just quickly explain.
I could. I think I can give you a hint. So what is A? A is a randomly chosen value that's doing the multiplication times the key. So that's like randomly choosing a step size around the circle. B is a randomly chosen starting position. So I know that if I just looked at the part that's in the box, basically what I'm doing is I'm shifting a circular like spirograph picture around the cycle, and I'm getting every one of the possible outcomes equally likely. So if I picked two different values for x, if I put in x or I put in y, and they were two different values, then I would get completely different values for the value that comes out of the box. They'd be totally different. But then I take it mod m. And the question is, when I take it mod m, does it actually preserve this property that it's equally likely to be any one of the numbers, meaning it has probability 1 out of m of colliding after I take it using mod m. But the point is that the first part, this part that's mod p, I can, there's a one-to-one mapping between the choices of A and B and the outcomes that I get from a one-to-one mapping between choices of X and Y and the outcome that I get from the first part after mod P. And so when I have probability of distribution now P times P minus 1 over the numbers of X and Y's, I can choose X to be one of P things and Y to be one of P minus 1 things. I get exactly the same distribution as I get for as long as X and Y are two different things, I get exactly the same distribution on the M. So I get probability 1 out of M.
Okay. So do we have to prove something like this on exam?
So the question was, do we have to prove anything like this on the exam? No. That's why I didn't prove it in class. When you take 420, then you'll prove this in class. And then you'll prove it on the exam. And then But it's not that hard, really. But I will ask you on exams to do stuff with modular arithmetic. And I will ask you, for example, to recognize when these figures occur, like clock figures, modulo figures. That will happen. Yep.
Speaking about the previous slide, could you quickly explain again what the spiral patterns were meant to represent? So do they just represent the possible inputs for k that we can choose to get unique values for the hash function?
The possible values of k are, I started with 0, And then I started calculating the hash function for 0, and then 1, and then 2, and then 3.
Oh, and then it's done repeating.
And if I did that, then I walked around the perimeter of this thing from going from the function when it was, this is when k equals 0, and then I went to where k equals 1, and then I went to where k equals 2, etc. So every one of those little arcs was a step around this clock. And eventually, those would come back and land on top of each other again. And that eventually, in the case of the mod 11, it's 11 steps later. In the case of the mod 10, it was 5 steps later.
Also, so the number of k values also represent the number of unique outputs that the hash function can produce. Well, like given like inputs 0, 1, 2, 3, you get unique values from the hash function.
That depends on your hash function.
Well, like in our example here.
Yes.
And for the second one, well, how come you say that the solution is 11 times I in this case?
I'm asking you what are the values of keys that would collide. And so try 11 and then try 22.
So keep hashing to 7, right? Is that the reason? Hold on.
Well, it depends. This 11 times I will, this is 11 times I that you plug in here. It will hash to 7 for I equals 0, and it will hash to 7 for I equals 1. It will hash to 7 for I equals 2. Yep.
So if you pick A and B randomly in the math line, so there's the possibility such that you get this first hash function you have in the first line.
Yes.
Which is another one, right?
No.
It's not bad.
Well, they're all bad.
Other-
If you fix any hash function, it's bad. The point is that you're choosing this at random. So nobody knows that you're going to pick that one. You'll pick something. But if after you pick it, you happen to tell everybody, hey, this is my hash function, then there's a problem. Because then you're giving them enough time to calculate something that will crash your server. But if you pick it each time you use the hash table, I mean, if you pick it when you build the hash table so that you always use that function for the hash table, you're okay. Yep.
You choose the functions at random when you want to look up the number associated with the hash. How do you do that?
Great. This is a great question. If I pick these functions at random, how am I going to look up the function? How am I going to look up in the hash table when I want to go and find something that's in the hash table? How does that work? Do I just generate it and hope that it's the same function I used when I put it in there? No. What do I do? When do I generate this hash function? I store A and B as well in the hash table. I generate the function at random. I generate it once when I build the table. But when you ask me for a hash function, and I'm the C++ library, I give you a hash function, but it's a randomly generated hash function that I'm always going to use for the table that you've just asked for. Unless you resize the table, in which case I'll change it. But it's always used. It's randomly selected and then always used after that for that table. These are all great questions. Hashing is mysterious. It's a wonder that it even works. Oh, we know about the birthday paradox. I just want to point out one thing. If you're gambling and there are 23 people at your party, this is a good way to gamble. It's like playing blackjack when you know the cards. But there's another thing that I wanted to tell you about, which is for perfect, unless you know the keys that are going to be hashed by your hash function, unless you're building a hash table for a fixed dictionary, in which case you can construct a perfect hash function. Unless you're doing that, you're stuck dealing with collisions. And so there are two main Oh, we have 5 minutes to talk about this. This is great. It's perfect. There are two main ways of dealing with collisions. One is chaining. That's where we stick them into the same slot and we chain them using a linked list. And the other is called open addressing, which you could also invent in 5 minutes if I forced you to on an exam. Open addressing says don't make any more space available, just use slots in the table. How will you use a slot if I'm hashing to a position that's already occupied? I'll just go to the next one that's open. So I'll just go hash to a spot and I'll say, oh, that one's full. Let me check the next one. Let me check the next one. Let me check the next one. Let me check. Oh, here's one that's empty. I'll put myself there. So it fills up the table in a different way. We'll talk about both of them, but first chaining. So this is where I have a linked list associated with the location in the hash table where I'm storing items, and when I put something in, it goes into that linked list. So this is great. Actually, this is fantastic design because you don't have to really worry about how big to make the hash table initially. You can make it as small as you'd like. And people might put in lots and lots of keys into the table, but it's okay. I can put more keys into this table than the size of the table. I just make my linked lists longer. It's fantastic. And there's some downsides in that I have to allocate memory on every single one of those insertions. I have to create a linked list node in order to put something into the table. If I didn't have to do that, that would be good, but okay. But I'm getting something for it. I'm allowed to have this table exceed the size of the number of keys in the table exceed the size of the table. It's good. When collisions occur, they're not a problem. I just check the linked list. But whenever I perform an insertion into the table, like in all hash tables, I should perform a find to make sure that that thing that I'm inserting is not already there. It's like a dictionary, and you don't want to put in multiple copies of something that has the same key. What dictates the performance of one of these chain hash tables is something called the load factor, which is simply the number of items that are in the table divided by the table size. So if that number is large, then the number of hashed items in each table slot is large. So this really is, it's like the average number of items per slot. And if I look at the cost to perform these different operations, like a search cost, a find cost, in a hash table that has a load factor of alpha, for whatever reason alpha is always used as a load factor. If I look at that, on average, if I perform an unsuccessful search, like I try to look something up in my hash table and it tells me, nope, it's not there. And that hash table has a load factor of alpha. And in addition, we have this amazing, amazing uniform hash function, which means it's equally likely to put every key into any one of the slots. So that's what this means. Equally likely to hash to any slot, which is an assumption that's not realistic, but we're going to make it for just to get an idea of how the performance degrades. What is the cost of doing an unsuccessful search into a hash table with load factor alpha? Yeah. It's just alpha. Right? Because you hash to a particular location, and that particular location has how many items in it? It has about the number of hashed items divided by the table size. So the amount of work you have to do in an unsuccessful search So you have to walk down that entire linked list, and that linked list has length about alpha. And so you get about alpha cost. The successful search is more interesting. It's so interesting that your book got it wrong. So anyway, it's very interesting. But it looks like this. It looks like the cost associated with finding the successful item, the one that you found, and then of all the other items, the n-1 other items in the table, half of them probably preceded the item that you found in the linked list. So of the ones that ended up in your slot, which was n-1 over m, about half of them preceded the item that I was looking for. And so the cost is 1 plus half of n-1 over m, which turns out to be something like this in terms of alpha. Okay, next time we will talk about open addressing, the other alternative.